Okay, so we know that glaciers do move, but if they're solid ice, how do they move? There's a couple ways that glaciers can move. All of them flow downhill under the force of gravity. Those that have a wet base, meaning there's water at the bottom of them between the ice and the land, that means they're lubricated, so they can just slide right over the top of the sediment beneath them. That's a wet-based glacier. However, some glaciers are so cold that that liquid water can't persist at the base of the glaciers. And instead, it's just solid, cold ice. There's no liquid in between the glacier and the ground. So instead of that glacier being able to easily slide over the wet ground, instead, the ice itself deforms. The solid ice flows. What I mean by this is that if you start with, think of a square of ice, over time, the top part of that ice is going to be able to flow while the bottom part of that ice is going to be stuck near that the rough surface of the sediment beneath, right? And this is what we call internal plastic deformation, right? This is going to involve recrystallization and stretching and rotating of grains, but the ice itself is going to be able to flow. This is the way dry-based glaciers move, but it can also happen in wet-based glaciers. Now, ice, it's a solid, right? So even though it flows, it can also fracture. And where glaciers fracture, they have huge cracks that we call crevasses. This happens near the surface of the glacier where they're more brittle, right? But they're huge. They can be so large that people can actually fall down into them. So this is one of the dangers of walking on glaciers, is accidentally falling down into a crevasse. Okay, so as I said, ice flows downhill under the influence of gravity. And it can even flow over a local incline, right? Even if there's a little bump, the ice can still flow over it. Think of it like you pouring honey over a bumpy surface. Even if there's a little bump, the honey is viscous enough, it can still flow over that bump. And the ice is going to flow downhill, but also radiate outwards in all directions from the thickest internal point. So again, think of pouring honey onto a flat surface. The honey is going to flow outwards in all directions. This is the same thing that a large glacier does. Now, as that glacier is flowing, any part that is in contact with rough sediment, the rough ground surface, that part is going to flow the slowest. But any part of the ice that is far away from that surface is going to be able to flow faster. And that's where we get that internal plastic deformation. And overall, the ice flows from an area of accumulation at high elevation to what we call the toe, which is at the low elevation. Okay. And the equilibrium line is what separates the zone of accumulation, where snow is falling on the glacier, we're accumulating ice, down to what we call the toe, the zone of ablation, where there's a net loss of ice due to greater temperatures, more evaporation, more melting. And this allows us to think about a glacial budget, right? All glaciers, or not all, but most glaciers are gaining volume up at high elevation, flowing downhill, and then losing volume at low elevation. The glacial budget is the balance between that, right? It's the balance between how much volume is being added and how much volume is being lost. If more is added than lost, the size of the glacier is going to increase, and it's going to have what we call a positive budget. If more is being lost than added, then the overall size of the glacier is going to decrease, and it's going to have what we call a negative budget, or a loss of ice. Now, due to climate change, most glaciers on Earth currently have a negative budget. They are still growing in the zone of accumulation, but more is being lost, more is melting. So you get an overall negative budget and overall net loss of ice.